Okay, so in this lesson what we're going to be doing is focusing on the graphing of exponential growth functions. And so we've already done our introductory activity, and what we're going to do in this is focus on two aspects. We're going to graph a variety of exponential growth functions, and we're also going to be looking at the domain and range of those exponential functions. Okay, and so we'll start off with a look at the form of the exponential function, which is really its equation. And what we'll notice is it's got a couple of components to it. We have y is equal to a times b to the power of x. A over here is just going to be the coefficient of our base. B is going to be our base, and of course x is our exponent or our power. Of course, in the place of y, we could very easily, using function notation, have f of x, h of x, g of x, any one of those notations which indicate that it is in fact a function. And then exponential functions have got certain key characteristics, and so hopefully you picked some of those up through the introduction activity. But in order for these functions to have those characteristics, there are certain restrictions to the base equation, the y equals a times b to the power of x. And so those are detailed over here. First of all, we have a cannot be equal to 0. So of course, if the coefficient was equal to 0, then we would not have an exponential function at all. So here we have an example. If we had y is equal to 0 times 2 to the power of x, with 2 as the base, x as the exponent, anything we're multiplying by 0, of course, gives us 0. Y equals 0 is simply a horizontal line, and this is not an exponential function. So that explains why we have the restriction that a cannot be 0. B greater than 0, that's a little more complicated to explain. We're going to leave that to a future lesson. But the second restriction we'll explain, or I'll explain right now, will be the fact that b, which in this case represents the base, cannot be equal to 1. And again, I'll give an example. If we had y is equal to 5 times 1 to the power of x, of course anything to the 1 to the power of any exponent is always going to produce 1. And so effectively what we're left with is y equal to whatever the coefficient is. Once again, that's a constant. It produces a horizontal line, and that is not an exponential function because it does not behave in the same way. So that's the reason that we have these restrictions. And as I said, the b, the base being a positive number, we'll explain that in a future class. Okay, so what we're going to do now is go ahead. We've got an example in function notation. F of x is equal to 3 over 2, or 1.5 to the power of x. So that there is no coefficient here, so the assumption is that it's 1. So the value of a in this case is 1, which is perfectly acceptable. And here we're dealing with a reasonably complicated fraction. And what we're going to do is, as we did before, and in fact a standard procedure is the use of a table of values. As mentioned in the introduction, x is the independent variable, and so we are choosing the x values, we are substituting those into the equation. And so of course an example would be f of minus 2 is instructing us to substitute in minus 2 in the place of x, and that in turn is determining the value of y, or f of x. So y equals and f of x equals are essentially the same thing. And this variable, the y variable, or the f of x, is of course the dependent variable because the value of y depends on the value of x. Okay, so the first of these is already underway. We've got f of minus 2, that's 3 over 2 to the power of minus 2. Using our laws of exponents, that's 3 to the power of minus 2, 2 to the power of minus 2. Using the properties of negative exponents, we can rearrange that as 2 squared over 3 squared, evaluate those expressions, and we get 4 over 9 as the value for y when x is minus 2 for the expression f of x equals 3 over 2 to the power of x. Okay, and so we'll continue doing this, substituting in the remaining 5 values to find the corresponding y values. Of course, keeping in mind that each time we're doing this, we're getting an x value and a y value, which make up a coordinate pair, a set of coordinates, which we are going to plot on the graph afterwards. Okay, so I'll show one more substitution. We have f of minus 1, which is 3 over 2 to the power of minus 1. Once again, 3 to the minus 1 over 2 to the minus 1. Use our property of negative exponents and move each one from the bottom to the top or the top to the bottom, depending on which number we're talking about, and we get our value of 2/3. When we substitute in f of 0, of course, any base to the power of 0 produces a numerical value of 1. F of x, or rather f of 1, is 3 over 2 to the power of 1, which of course is just 3 over 2. And then our last two, f of 2, means we are taking our base 3 over 2 and we are squaring it. So 3 squared over 2 squared, which simplifies as 9 over 4. And last but not least, we have f of 3, which is going to be 3 over 2 cubed, 3 cubed over 2 cubed, and that gives us a value of 27 over 8. Okay, now what we'll do is we'll go down and we're going to plot each of those points onto our graph. And so we begin, I'm going to plot this in red. So we have the x value of minus 2 and the y value of 4/9. So here is our x-axis. At minus 2, we have a y value of 4/9, a little bit underneath 1/2. So if that's approximately where 1/2 is, our point will be just a little bit underneath. We have the next coordinate point. X is minus 1, y is 2/3. So we go to minus 1 on the x-axis, a little bit above a half for 2/3. Our third point, when x is 0, y is 1. And so right here at the origin where x is 0, we have the y value of 1. When we have x has a value of 1, we have our y value of 1.5. X equals 2 produces a y value of 9 over 4. So 9 over 4 as a decimal is 2.25. And so we're going just a little bit above the 2. And our final point from the table of values is x equals 3, y equals 27 over 8, which if you type that into your calculator would give you a value of 3.375, so a little less than 3.5. And so when x is 3, y is going to be right around just underneath 3.5. So now what we're going to do is to complete the graph, we're going to join those points as carefully as we can without using a ruler. Of course, this is not a line. Exponential functions do not behave the same way. We should not be using a ruler for this. Again, rulers are for lines or linear functions. So I'll draw this as smoothly as I can, making sure that I pass through each of the points that I've plotted. And you'll notice the shape of the graph as it curves up, and then I'm just going to put an arrow on each end. Of course, you can see from the table of values we've got a fixed number of x values, but of course there's no reason that we couldn't have values of 4, 5, 6, 7 and upwards, and likewise minus 3, 4, 5, minus 10, minus 100. And practically speaking, of course, we don't want to have to graph too many values. This gives us enough to know the shape of the graph. What we'll do is just add in a few important details, label a couple of our points. So x is 0, y is 1, and we'll also label the point x is 2, y is 2.25, and of course we must label our function, and our function was f of x equals 3 over 2 to the power of x. So that completes our graph. And now what we're going to do, just to finalize the example, is to answer the questions: what is the domain and what is the range? Okay, as I mentioned above, x represents the independent variable, and when we talk about domain, we are talking about the values of the independent variable. When we talk about range, we are talking about the values of the dependent variable. Okay, and so essentially for our domain, in this case, we are talking about the x values, and in this case, x is an element of real, which really means x can be anything, all values, any value from anywhere along the number line, and hopefully that's made clear by the fact that we have the arrow on either side of the function indicating that it's continuing forever in both of its directions. Similarly, we're going to write down the range. The range is the set of y values represented by the graph, and as you can see, the graph goes up, it's increasing, and as x grows, it's going to continue to increase. The y value is going to continue to increase. This is an example of a growth function. As the value of x, the independent variable, increases, the value of the y also increases. So this is known as a growth function, and you can tell that it's a growth function because you will have a base which is larger than 1. Our base was 3 over 2, 1.5, and you also have a coefficient which is a positive number. In this case, our coefficient was 1. Okay, and so if we look at the range, what we'll see is as the value of x increases, the value of y increases. But if we look to the left-hand side over here, what's happening as the value of x decreases, becomes -6, -10, and so forth, what we're going to get is a fraction which is going to get smaller and smaller, but it's never going to become negative. There is no way. Remember, a negative exponent means a fraction. It does not mean a negative value. And so what's going to happen is the graph is going to get infinitely closer to the x-axis, but never touch it and never go underneath. And so for our range, we have y greater than 0 or all positive values. Okay, so this should put you in a position in terms of understanding and method to go ahead to the second page of your note and to go ahead and fill in the table of values for the 3 functions that have been given to you, and then to determine their domains and their ranges. Once you've completed that, then you should watch the second part of the video, which will give you the answers to those examples to make sure you've done it correctly, and will also I'll make a brief reference to some of the uses of exponential functions.